Good evening, dear students. Today we will be discussing, mathematical reasoning in continuation of whatever we have discussed in the last couple of sessions. So today we will start with quantifiers. Now, before I proceed further, could you please confirm that you are able to hear my voice very clearly and able to view the screen properly, dear students?
Yes, sir.
Okay, great. Thanks for the confirmation. So, what are quantifiers? Quantifiers are phrases like there exist, for all. These are quantifiers. In mathematical notation, there exist is represented by a symbol I'm going to show you, and for all is also represented by a symbol, and I'm going to show you those things. Okay. If you see the quantifiers, okay, there exist and for all. So let me first connect to the digital board. Just give me a second. So there are two quantifiers. One is that there exist, and it is denoted by this, that is called there exist. And another quantifiers is for all, and that is denoted by this, or you can think of there exists is denoted by, if you take that that E and takes a mirror image of E, whatever you will get. And A is for all, it is, that is a, if you flip A, then whatever you will get. So we are going to see the implication of this thing and where it has been used. So if you see that we say something like this: for all n belongs to the set of natural number, what we can write? 1 plus 2 plus 3 plus ... up to n is equal to, if you recall, it is n into n plus 1 by 2. So here we have used that for all n belongs to n. Okay. Now another point what we can, so this is one example of using of the quantifier called for all. And there is another quantifier we can say is that there exists a vector whose direction is arbitrary. There exists a vector whose direction is arbitrary. Okay, dear students. Now that is what is known as the quantifiers. So as I have explained you what is meant by quantifiers, now let me tell you the fundamental definition and these two examples, whatever I just said, and by taking it from our study material. So as you see, I placed in front of you that portion of the study material, that quantifiers are phrases like there exist, for all. These two are the quantifiers. And in mathematical notation, there exist is represented by that mirror image of E, and for all is represented by it is a flipped A. Sometimes we get mathematical statement containing these quantifiers, as I showed you, and here also it is written. Now, dear students, what we are going to discuss, we are going to discuss about the validity of statements. And that is also a very important topic, that what is meant by validity of a statement and its different, subtopics that we are going to discuss now. So, dear students, let me take you to the new page and explain you about the validity of statements. Validity of a statement means checking when the statement is true and when it is not true. I repeat, validity of a statement means checking when the statement is true and when it is not true. Validity of a statement depends upon which of the connectives, quantifiers, and implications is used in the statements. And we'll see all these things. So, dear students, whatever I just discussed, let me place in front of you. And here it is. That validity of a statement means checking when the statement is true and when it is not true. That is the validity of a statement. I hope you understood this part. Now, validity of a statement depends upon, connectives, quantifiers, and implication which has been used in the statements. So, let me give you an example of validity of a statement with and. Okay, so validity of a statement with and, what it is, let me show you. So if you remember that connectives for and is something like, this thing that and a symbolic notation. This is and one, P and Q. To show that P and Q is true, we need to show that P is true and Q is true. When both are true, then only P and Q is true. If you recall the truth table of the connective and. Now, I'm going to tell you the validity of a statement with or. And here it is. The validity of a statement with or is something like that. To show that P or Q is true, we need to show that either P is true or Q is true. Either P is true or Q is true. All right. And if you recall the truth table of the connective or, then it is very clear to you. So this is the way we represent that or. So P or Q is true when we say that either of P is true or Q is true. Then only you can say that P or Q is true. So that is the validity of a statement with or. Next one is that what we are going to discuss is the validity of a statement with if then. So validity of a statement with if then I'm going to discuss with this one. So if then means what, dear students? If you recall in our previous session, the lectures are available in YouTube as well as in the online platform. To show that if P then Q, then any one of the following method has to be followed. Let me show you this thing. Okay, let me first place this statement. To show that, to show if P then Q is true, we need to follow any of the following methods. The first method, dear students, is called the direct method. Assume P is true and based on this assumption, so that Q is true. That is, it is the implication. P is implying Q. The second method is called the contrapositive method. We discussed in details about contrapositive method in the last class. So what is contrapositive method to, here it is, okay. Second one is contrapositive method. So assume that not Q is true and based on that assumption, so that not P is true. That means not Q is implying not P. Okay, so that is the second way of to show that if P then Q. And the third one is that contradiction method. What is a contradiction method? Let me first place the statement in front of you. After that, I will explain. So contradiction method says that assume that both P is true and Q is false. And then based on that assumption, deduce a contradiction. That means what? Deduce something which is not valid anymore, which is absurd, is of no meaning. That is what is called contradiction. So in context to our our discussion, that is if P then Q is true, the contradiction method should be that assume that P is true and Q is false. What we had to show that if P then Q, if P then Q is true. So here what we are assuming in the method of contradiction, that P is true but and Q is false. That means if P then Q is false. That is our assumption. And with these assumptions, what we deduce is that is a contradiction to the given result. Okay, contradiction to the given information. Then you can say, yeah, whatever our assumption was is wrong, hence it is not true. If you recall a very classical example I always give and which you are always aware, recall in your previous year we discussed about that. Okay, prove that root 2 is an irrational number. To prove being that root 2 is an irrational number, what you did, dear students, you first assume that if possible, let's take root 2 is a rational number. And with that assumption, you reach to a conclusion which is very absurd, very absurd. Okay, that means you get there is a common factor between the PQ where root 2 has been expressed as P by Q. The moment it is a rational number, you know that HCF of P and Q has to be 1. But with that assumption that root 2 is by the assumption that root 2 is a rational number, what we got is that there is a factor between P and Q apart from 1, which contradicts to the fact that root 2 is a rational number, like that. So that is what is called contradiction method. And the next one is that, and that is what is called giving a counter example. And how to do this thing. So let me give you the statement first, and after that I will explain further. So here it is to giving a counter example. Okay. In case we need to disprove a certain statement, we just need to give a counter example to validate that statement is false. Let us take the example. We need to disprove that all prime numbers are odd. And to do that, we need to take a counter example like 2, which is even, but at the same time it is a prime number. So that is by taking a counter example, we can also establish. Now, dear students, one thing I would like to inform that to prove a statement, illustrating the validity of the statement by means of an example will not sufficient to prove that the statement is correct. So what does it mean is that when we need to disprove something, a counter example is sufficient. Okay, but when you need to prove something, just giving one example is not sufficient. Okay, then you need to prove by means of a conventional method. Okay, for example, I can give you an example is that, if you need to prove the Pythagoras theorem. So if you recall, the Pythagoras theorem is what? Is that, we know if this is, A, this side is A, this side is B, and this side is C. We know what? C square is equal to A square plus B square. That is the Pythagoras theorem. Now, if you need to prove Pythagoras theorem, if you just take one example of ABC, that is not sufficient. For example, if you take the value of A as 3, B as 4, and C as 5, you will be able to prove it. 5 square equal to 3 square plus 4 square. Now, by just proving that 5 square equal to 3 square plus 4 square, you are not able to prove Pythagoras theorem. You can only make a validity that yes, Pythagoras theorem is working for this right angle triangle where the three sides lengths are 3 units, 4 units, and 5 units respectively. Now, to prove, only one example is not sufficient. But if you need to disprove something, like so that if you take the any triangle, for any triangle, if you take another triangle, suppose if I draw in a different color, suppose you take a triangle something like this. So if we take P, Q, and R are the length of these three sides, so always we know that P plus Q is always greater than R. Q plus R is greater than P, and R plus P is greater than Q. Now the point is that if you have been given on three values, and you have been asked that can you show that whether you can construct a triangle or not. Only thing is that we just take one counter example, take these three values, and just if you are able to prove that sum of that any two is less than the third one, then you can say it is not possible. Okay, that means these three has to be satisfied that a triangle to be constructed. Okay, but by somehow you can prove that P plus Q is actually less than R by means some example, sufficient. That is sufficient to prove that you are not able to construct a triangle. Okay, so that is why when you need to disprove something, what I'm saying, when you need to disprove something, one counter example is sufficient. But when you need to prove something, counter example is not sufficient. You need to prove it in a very generic manner. Okay, dear students, so that is all about what I wanted to discuss about the validity of statement. Now, the last point what I'm going to discuss is that validity of a statement with if and only if, that is known as IFF. And it is very important, dear students, in lot of mathematical proof that validity of a statement by means of if and only if is extremely important. I will show you some examples that why it is important. So what is this that by means of if and only if? Let me show you. Let me first give you the statement, and after that I will explain you in details. So to prove that P if and only if Q, what does it mean? That when we say, I can write it here also, dear students, that we can write that P if and only if Q. So this is statement P here. This is another statement Q here. And what you get in between is that if and only if. And that is also known as P IFF. If and only if also written as IFF Q. So what is meant by that? P IFF Q. It means that to have the statement Q to be valid, okay, P has to be valid, and vice versa. That if the statement, P to be valid, Q has to be valid. Or the other way, what we can say, the step one is that assume P is true, and with that assumption, you need to prove that Q is true. Now, this condition is known as the necessary condition. Now, the step two is that it is a completely the reverse one. Assume Q is true and then so that P is true. This is known as the condition as sufficient. Both the above steps, jointly represented as necessary and sufficient conditions. So both these two steps are, uh, jointly represented as necessary and sufficient conditions. Let me give you an example, dear students. Okay, so that it will be very clearly understood. Okay, so let me take two statements. P, we can take the triangle ABC is equilateral, and the another statement Q, we take the triangle ABC is equiangular. Okay, now if we assume that P is true according to the step 1, if you look into the step 1, means if we take that P is true, step 1, let me write it down here, dear students, that step 1, what is step 1? That we are assuming that P is true. That means we are taking that triangle ABC as equilateral. Now with that assumption, okay, what we are able to prove that this is implying that Q is true. So we are able to prove that the triangle is also equiangular. So what is step 1, dear students? By assuming the triangle is equilateral, we are able to prove the triangle is equiangular. And what is step 2, dear students? Step 2 is that we are assuming Q is true. That means what? We are assuming the triangle is equiangular. And with that assumption, we are able to prove that P is true. That means the triangle is equilateral. Then we can say that P, as both these statements are holding true, so from here what we can say is that P IFF U. That means that this condition, both necessary and sufficient condition, these two steps, step 1 and step 2, jointly representing that the conditions are both necessary and necessary and sufficient. Okay, so what is necessary condition? That the triangle ABC is equilateral. It is necessary to show that the triangle ABC is equiangular. And when we take that assumption that ABC is equiangular, and then we are able to prove that ABC is equilateral. So here what it is? We are assuming that ABC is equiangular is sufficient to prove that ABC is equilateral. That is called the necessary and sufficient condition. Now, dear students, let me give you a very practical example. Okay, very practical example so that it will be very clearly understood that where the statement if and only works and doesn't work. So suppose there is a statement P. Okay, so let me write it down here. Okay, so the statement, let me use a different color. Suppose I use a color something like green. So what is our statement? P, it is raining. It is raining. And Q, the statement is road is wet. Okay. Now suppose that, dear students, we are having this class online. Okay. Think about that we are having all this class in a classroom. Okay. We are having this class in a classroom where the windows are closed, AC is running, so that there is no suffocation. Now once the class ends, I just open the window and looked outside, and I'm telling, hey, dear students, it is raining outside. Then what statement you generally make? Oh, sir, then road must be wet. The moment I say it is raining, your reply comes is that a road is wet. That means what? What we can say, dear students? That if P is true, okay, P is true is implying that Q is true. Because if it is raining, must be the road is wet. Yeah, obviously we are assuming that there is no, there is no arrangement that entire road is actually, completely, covered. That is impossible, right? It's impractical. We should not take that kind of a impractical assumption that entire road, a 100-kilometer road, suppose, is completely, covered, so that rainwater will not come. It is not possible. So we are not assuming that thing. Correct. Now, suppose in other day, what I am doing is that, we are also having a class some other day, and similarly the entire door and windows are closed, AC is running, so that there is no suffocation. We are having class, and at the end of the class I open that window and I say, hey, dear students, road is wet. The moment I say road is wet, someone can say, sir, it may be raining. Someone can say it may not be raining. There could be some other reasons that road is wet. Okay. We are having class in Bengaluru. In Bengaluru, there are water tankers, run every day. Sometimes water tankers, that hose pipe sometime open. Because of that, road can be wet. Okay. Or maybe some oil has been spilled on the road, because I am looking into a part of the road. So when I say that Q is true, in context to this example, when you say Q is true, that not necessarily mean that P is true. It may not. But in contrast to the previous example, if I say that Q is true, that is ABC is equiangular, definitely ABC has to be equilateral. And the previous one, if we say ABC is equilateral, definitely ABC has to be equiangular. But here, we see one counter example. If it is raining, definitely road is wet. But if road is wet, that doesn't guarantee that it is raining always. It could be some other reason. Rain is one reason, but rain is not the only reason, what I'm telling. So, on the other context, what we can say is that it is raining is the necessary condition to have the road wet. But the road is wet is not sufficient condition to assume that it is raining. Okay, dear students, I hope you got a fair amount of idea about if and only if. In mathematics and in other branches like in computer science, especially in theoretical computer science, the application of if and only if, that is IFF, is extremely important. So with this, I would like to conclude the class for today, dear students. In the next class, we'll make some practice from this chapter and other chapters also, and we'll continue. So from the next class. So unless you have any specific question for me, we can complete the class here. Thank you very much. Thank you.